Our next speaker is Chris Sinderby from Toronto, who will talk us about patient-triggered modes and how active is the patient.
Thank you. Before I start, I would like to thank the committee and the chairman for inviting me here. I will try to give a short presentation here to show how active is the patient in the on the mechanical ventilator when he is on a triggered mode. And to begin, I would like to show this graph, which is from Beck et al., which shows the diaphragm electrical activity over time, the volume that is delivered to the patient, and the transpulmonary pressure. This blue dashed line shows with the low pressure support when the actual peak activity of the diaphragm is reached and what volume we have. This line shows with at low pressure support what the activity is when the peak volume is reached. Now, increasing pressure support, we get the new line here and a new line here. Now, if we look upon the inspiration that is actually performed during low pressure support ventilation when the diaphragm is active, this is how much ventilation we get, that's the volume. If we compare with high pressure support, we get less active activation, but there is not much difference. Now, the passive part of the, of the inspiration, we call it passive, we don't have a better word. This part is relatively small compared to the active part with low support, but it doubles when we increase the actual pressure support. So in this case, we can conclude that passive ventilation increases with increasing levels of pressure support ventilation as a consequence of increasing cycling off asynchrony. I don't think this is really any news to anybody. Unloading during patient ventilator synchrony, though, becomes a different issue. And to show this, I want to show some work we've done in Toronto. And this is using neurally adjusted ventilatory assist. The system uses a nasogastric tube to measure diaphragm electrical activity, which is illustrated here. It sends the signal to a processor. The processor controls the ventilator, which feeds back the pressure to the patient. Now, this is 3 different maximal inspirations in a healthy subject. And you can see the inspiratory capacity volumes here. They are done with no assist and with increasing gains of NAVA. And this is the highest gain we had. The pressure here is 60 as peak pressure. This is a healthy subject doing TLC. Now, the transdiaphragmatic pressure is going to 60, or not 60, it's 45 in swing during the unassisted inspiration. With increasing assist, the PDI disappears. So when we have high assist, we have no more PDI. Now, the esophageal pressure is also going positive, suggesting that we are also probably compensating a lot for the chest wall load. Now, what happens to the diaphragm activation? Well, it goes down, but it doesn't go away. It stays up. So if you remove the load, your diaphragm doesn't stop to output signals. So mechanical unloading is not a measure of reduced neural drive, and that's very important to remember. Now, since time is short, I will just try to exemplify on a group of patients with COPD that we have studied, and that is during pressure support ventilation. First, before we start, I would like to show you how does the EMG look in a healthy subject. This is half-liter tidal volume tracing over time. This is the diaphragm electrical activity, and it's about 7% of the maximum activation. Go to a COPD patient who is an outpatient living at home with a PCO2 of approximately 43 to 45. The diaphragm activation is 5 to 6 times higher for the same tidal volume. And why? Because he has to recruit his muscles to get the air into his lungs. So severe COPD patients are used to very high levels of diaphragm activation when they are not treated in the ICU. Now, here is a pressure support ventilated COPD patient in the ICU. Now, can anybody here tell me how active is this patient? We have the flow tracing, looks nice. We have a volume tracing, looks nice. We have airway pressure, doesn't look too bad. Now, we put the diaphragm electrical activity at the bottom. First breath we see here, nicely synchronized, pretty good activity. The breath over here, though, seems to be a slightly lower volume, but the effort is nothing. And here we have a wasted effort that I think few of you had picked up. So airway flow, volume, and pressure does not monitor changes in activation and patient-ventilator interaction in COPD. Now, here's another tracing. And I'm quite clear that you can see that there are wasted efforts going on up here, the way the arrows are. So what should you do? Put a more sensitive trigger? Well, looking at the esophageal pressure, when the ventilator starts, the esophageal pressure goes totally positive. So this patient is on control mode ventilation. His diaphragm activation is barely visible, but you see the wasted effort had an EMG, and also the effort that started the ventilator had an EMG. Now, we have lowered the assist in this tracing. Now you see the breathing frequency went up dramatically. And we look upon the esophageal pressure. Now it's negative, and there is lots of diaphragm activation, and it's synchronized. So a small decrease in assist rather than increasing trigger sensitivity may improve synchrony and activation in the COPD patient. Now, in this slide, I want just to show if we connect the patient so that we let the assist be controlled by the diaphragm electrical activity instead. So we are turning back the electricity from the diaphragm to the ventilator so you get the assist that is proportional to the activation. And simply what you get is the ventilator starts when the activation starts, it delivers while the activation goes up, and it stops when the activity goes down. So neurocontrol may overcome problems of pneumatic controller systems. So in conclusion, how active is the patient? Well, one can be misled if using measures of airway pressure, flow, and volume to determine how active the patient is. Diaphragm electric activity may add valuable information. Thank you very much.